So again we have to build computing systems. Some of them are very complex. So when I told about sorting n numbers, this is a very simple problem, but modern computing systems like that you see in a smartphone, like it can do an enormous amount of various kinds of complex computations, right? So the traditional way to look into these systems is to actually break them up and look into the building blocks, right? So that is the procedure that we are going to follow in this course. So we want to look into what is fundamental, what are the fundamental building blocks of the super complicated piece of hardware, right? So if you take a smartphone like this and open it up, right, you will actually come across a lot of PCBs, right, printed circuit boards. So inside it you will find maybe 8 to 10 PCBs in a given device, right? So even as you can see, these PCBs are immensely complex. So if you look into these PCBs, all these PCBs are going to have some integrated chips, right? ICs we typically call it, and there are like maybe 8 to as many as 20 ICs in a complicated PCB, right? So this is not the end. Even the ICs are very complex. As you can see, there are many different things as you can see. So you have to look into this IC, and these ICs are going to constitute of things like modules. Okay, so if you look into a given IC, there could be maybe about 8 to 10 modules, such modules. So all these things, if you see, they are some kind of an increasingly complex computational block. Okay, let us complete this chain, and from a module, if you see, there is this concept called cell, which is again much more simpler than what an IC does, but you need maybe 10,000s of such cells or 1,000 of these cells in a given module. Okay, and if you look into zoom more into a cell, you are going to find out that a given cell are going to be some kind of a logical computation, and that is made using some logical gates. Okay, we are going to introduce you to what these gates do, right? Some kind of logical operations that you are already probably familiar with, like AND, OR, XOR, NOR, and so on. Those are implemented by gates. And if you see how are gates themselves implemented, gates are actually implemented using transistors. Okay, and each and every transistor is going to be having a state on or off, which is often called switching. So digital information, as we see today, typically is abstracted by the zeros and ones, but this is really not zeros and ones, but this is two kind of switching states. Either it could be on or it could be off, anything that has two values, okay, or two states. So a transistor, for example, can have these two states. It could be on, it could be off, and starting from that, like you can think of being on is like a circuit. You can think of, if I want to really clarify what I mean by on, we can imagine to be this is a wire that is carrying some kind of, let's say, electricity, and whenever you switch it off, you restrict the flow of electrons. Whereas once you, if you switch it on, right, if you make this, join this connection again, so here electrons won't flow, whereas in this case electrons will flow. So you can think of this as a, let's say, open state, and you can think of this as a closed state, right? So you can literally see that the orchestration of the electrons in action, right? Because once the transistor is kept on, the electrons will flow, whereas whenever it will not flow if it is open. If it is closed, the electrons will flow, right? And this is going to be there is going to be used multiple such transistors to create things like this logical gates, right? We are going to learn more about gates, but as a part of this lecture or as a part of this course, we are not going to look into how are gates implemented using transistors, but you have to believe me that these transistors could be used in various combinations to create these gates. If you are really interested, you can look into the Harris and Harris book and actually see how logical gates could be implemented using such transistors. But once you know that you have these building blocks called gates, I would say logic gates. Once you have these gates, you can actually combine these gates to build various modules, right? So in the start of this lecture, I spoke about adders, right? You can have number A and you have a number B, and you can have a circuit, or let's say a module, that can take A and B and compute A plus B, right? So this can be a small cell, right? And that is going to be implemented by a collection of gates. Okay, so that is going to constitute of a very small functionality. Okay, and similarly you can have this many adders, maybe to implement something that is much bigger. Maybe it can add large numbers, right? Or you can think of a circuit that does multiplication, but again you can think of multiplication as a repeated addition, right? So for creating a module that does multiplication, maybe you need many such adder cells. So these are little bit hypothetical examples, but I am trying to make the point that how this increasingly complex hierarchy can be used to build something which is much more complex, like a smartphone, right? So keep in mind of this entire flow diagram. So starting from transistor, you can go to gates, from there you can go to cells, from there I can go to modules, and many such modules can be constituting an IC, and typically PCBs are collections of such ICs, and very complex systems like robots or your drone or all the modern computing systems you saw, they will have invariably have some of these PCBs connected together. Okay, and even one such IC could be your processor. Okay, there could be many ICs for handling memory, for interfacing with sensors or the sensors themselves, and one of them could be the processor itself. Okay, so we saw how these transistors could be clubbed together in form of gates, and then in terms of modules, how such modules are used to build an IC, and how you get and eventually you get an PCB which is going to do a very complex computational job. So now if you see, this entire computing system is basically a business of managing billions of transistors, right? Why billions? You can do a very simple calculation that here you have tens of transistor, here you have tens to 20, right? Let's say tens. Here you have almost 10 to the power 4, here you have 10, again you have 10, you might have 10 here, right? So it is like 4 plus 1 5 plus 1 6 plus 1 7 plus 1 8 plus 1 9, right? It's kind of 10 to the power 9 sort of range we are talking about. So literally it is not just thousands or lakhs or crores, even more, right? It's kind of hundreds of crores or more than that, right? So we are talking about managing billions of transistors. It's not millions, not hundreds, thousands, and so on. So typically managing them is referred to as or designing a circuit which consists of such high number of transistors are called, such ICs are called very large scale integration circuits. They call VLSI circuits, right? So this is by no means a part of this course, but somebody who is getting introduced to computing systems for the first time, they should keep in mind that this is a very complex procedure from fabrication, where we have to literally embed or kind of orchestrate or manage all these billions of transistors in a very small area, right? You will not see IC that is of the size of your bedroom, right? It's always going to be a few centimeters by, or maybe a few tens of millimeters by a few millimeters, right? And within that, so many transistors are packed, right? So you can think of the enormous complexity of the process. And given that this process is becoming more and more efficient, more and more power efficient also, you are having smaller and smaller such devices, right? You can pack in more amount of computation in the same form factor. So if you think of that Nokia example that I gave you, so the Nokia 3310 phone and a smartphone today may be of comparable form factor, maybe a little bit here and there, but they are typically kind of a form factor that could be held in your palm or in your hand, right? So but they have a huge difference in the computing power, because the amount of transistors that was packed in the ICs that was there in Nokia versus that is there in the Google Pixel smartphone, there's a lot of difference, right? So with the betterment of these technologies like for fabrication or VLSI, these things become more and more efficient, and more compute power could be packed in smaller and smaller form factor devices. Okay, so this is just a point, and as a historical fact, you should remember this law from Moore's, or called Moore's law, because why this so many transistors are being packed into this integrated circuits. So there is a anecdotal reference to this Moore's law, which is termed by founder of Intel, right, Gordon Moore. He recently passed away, I think, in the last year. In 1965, there was a this observation that he has made, that the number of transistors in a dense integrated circuit doubles about every 2 years, right? So you can think of the number of transistors being proportional to the computational capacity. So if you think of an IC in the early 1970s, every 2 years the number of transistors inside that IC, you could basically pack in more transistors, right? It's not that it just doubles, right? The technology advances such that the transistors become smaller and smaller and more power efficient, maybe, so that you can pack more number of transistors in the same form factor of the die of the IC. Okay, so this is one of the seminal articles, and it has been highly referenced, right? It's cramming more components into or onto integrated circuits by Gordon Moore, right? So he was the person behind Intel, right? He was the founder of Intel, right? So this Moore's law kind of reflected earlier. So currently we are in the post Moore era. This is no longer true post 2020 or even mid 2010s, right? Where it no longer doubles uh, because of many reasons. The power dissipation, because if you cram too many such transistors in a integrated circuit and you increase the number of them every year or every 2 years, the power dissipation has to be taken care of, because all these transistors also dissipate heat while doing the computation, and this heat has to be somehow absorbed or somehow taken out of that IC, right? Otherwise the things will melt or burn or so, right? So you cannot indefinitely do it, and we have already seen the kind of an age, we are already in an age where Moore's law is no longer valid, right? So this is more for an historical reference. During the evolution of computer chips, this was a very nice observation that has been made, right? And this was true for the last 50 years or so, right? And if you see this history of shrinking chips, right, when the first transistor was awarded the Nobel Prize in 1947, it was just a huge looking bulky transistor, only one transistor, right? And they made the first silicon transistor, the semiconductor transistor, in 1954. The first CMOS gate, right? CMOS is complementary metal oxide semiconductor. So this is a special kind of transistor, and that has been historically used for all the modern to build all the modern microelectronic devices using transistors and so on. So the first CMOS gate was built in 1963, the first commercial CMOS chips in 1974, and at that time digital watches were made, because digital watches was using some amount of electronic circuitry, and they were using the CMOS chips. That was as early as 1974, right? And as of 2020, some of the largest chips in the world have so many transistors, right? So this is like 10 to the power 10, which is more than the number of people on earth, right? So if you look at the trajectory, the year of introduction versus the number of transistors per chip, you see that this is a super linear scale, right? This is 10 to the power 3, which is in thousands. uh, this is like a million, right? 10 lakhs, this is like a crore, and so on. So if you see how things have evolved over time, and if you think of the form factor of a let's say a Pentium chip or a Core 2 Duo chip, or the form factor did not change much, right? It is typically something that you have already seen in your motherboards, the processor resides. It's the number of chips that has the number of transistors that are going into the chip, or the density at which these transistors are packed inside the chip, that has gone up, right? So now we have already started seeing some amount of slowdown, right? But this was true for, as I told you, for the last 50 years or so. Okay. So you might think that we will teach a lot of computer hardware as a part of this course, although the BS data science, it's more software focused, but there are a lot of things where we try to design computer systems and from the grounds up. So these are some things that will deal heavily with computer hardware, and once you take a course on operating systems, that will show you the software side of things. And of course, to develop better software, you need to understand the hardware and vice versa. So in order to design better hardware, you need to also understand how the software works, right? So with a combination of this course, your operating systems course, as well as things like computer networks, where you are going to have a substantial amount of introduction to how these computers communicate among each other, you are going to have a holistic understanding of a modern computing system, because you cannot do away with each like nothing that was mentioned, like an operating system, a networking component for communication, as well as the bare hardware. So all of these are fundamental building blocks of a modern computing system, both in terms of hardware, software, communication, and so on. So in this course and future course, for example, if you take a course on advanced architecture, so organization, we are going to cover some here. So advanced architecture, operating systems, compiler design, computer networks, embedded systems, VLSI, and so on. This will take you into a journey of exploring the area of computer systems in a broader sense, right? So you will know more about hardware and software interfaces, microarchitecture, and understand the trade-offs that I said, right? Which architecture would be preferred for a given computing task over another architecture? Why do you choose a particular kind of an architecture, right? It's not always just for computational efficiency or decreasing the amount of time needed to do a computation. Sometimes you need to take into consideration things like how much power the device is going to consume. Maybe the device is a battery operated device, right? You cannot really have a power source from the grid to power the device, so you cannot spend too much energy doing this computation, right? It has to be done in a power efficient way. So depending on what kind of uh, parameters or what kind of performance indicators we want to optimize your design on, that will lead to a specific kind of an hardware software combination, architecture, and so on. Okay, so this is, we will start our journey. This is an introductory course that will help you grasp some of these concepts, and you can take it forward once you take the more advanced courses. So we will understand these things bottoms up, as I told you in the previous slide, where we showed that how transistors form gates, and gates form modules, cells and modules and ICs and so on. So you saw already the plan of attack that we have is more of bottom up, right? We start with the fundamental building blocks of a given circuit and work our way upwards. Okay, and we want to encapsulate our understanding using appropriate abstractions. So what does it mean? So we were trying to abstract out a collection of gates using a cell. Once we say cell, that cell has a certain functionality. Let's the cell does the work of an adder. Okay, so once we abstract out that okay, this is an adder, we won't question how the adder is implemented. The adder has an internal details, right? The adder, it is more of your object oriented design thing that you may have come across, that this is an adder, and this adder, if it is given a and b, it returns a plus b. This entire thing is encapsulated in this building block called an adder and implemented using gates, right? So we will understand how things work starting from the gate level to more and more complicated modules. So you will be able to conceptualize and design simple digital logic blocks that work as the building blocks of a computing system. As you will see later, once we start designing computing system, a processor, ALU and so on, all these simple building blocks are going to be kind of pasted together in order to form the bigger circuit or the bigger picture, right? So you'll be able to design a simple, of course it is not a very complex computing or a complex processor that you see in a modern day computer, but you will get a good feel of how these things work at all, right? So you will be able to design a simple CPU consisting of an arithmetical and logical unit. We are going to come into details of what an ALU is, how does it work and so on, timing and control units. So we will use these simple digital blocks to create a simple CPU, okay? And just to give you a brief idea of what is an ALU, ALU is the block within the CPU that does the actual calculations, right? For example, if you have an arithmetic calculation, you want to add, you want to subtract, you want to increment a number by 1, you want to decrement a number by 1, you want to multiply, you want to divide. Typically, these are implemented in hardware. You have an adder circuit, you have a let's say a multiplier circuit that resides inside the ALU and does this job, okay? And similarly, there is a logical part of ALU that does some of the logical computations. Let's say you take two inputs and find out their logical AND, right? So you AND those two bit streams, right? Or you want to do an XOR, or you want to do a complement of a bit, right? So these are the logical primitives or arithmetic primitives that are there inside the central processing unit, and the CPU is basically going to coordinate the entire process of getting all these inputs A and B, passing them on to the ALU, instructing the ALU to compute the desired output, and communicating this output to wherever it wants to send it. It could be either in an internal register, or it could be writing it to some external memory and so on, and then fetching the next instruction, getting the next instruction and executing it, right? So the central processing unit is tasked with executing a program, and it is done. Some of the arithmetical and logical primitives are implemented as a part of ALU, and we are going to learn how our ALU is implemented using this simple digital logic blocks. So we are going to first understand how these digital logic blocks are created or implemented, what are the design principles. We will create some of the digital logic blocks ourselves, and then move forward to create more complicated systems like ALUs, right? And further complicated systems with that has timing and control to create an entire CPU, okay? So module 1 is going to be the lesson that we are currently having, the abstractions, foundations, what do we mean by digital, why is information represented digitally, what are logic gates, some introduction to Boolean algebra and computer arithmetic. So certain things might not be sequential. We will study Boolean algebra, maybe computer arithmetic is going to come up when we go more in an organization part. So this is about module 1. Module 2 is strictly going to tell us how we are going to go about designing uh, some kind of logic called combinational logic. I am going to clarify that later, and eventually leading us towards design of an arithmetical and logical unit. Module 3 is going to be the design of sequential logic elements. So just note the change in terminology. This is a combinational logic element, whereas this is a sequential logic element. Don't worry about about their meanings right now. So sequential logic has something to do with dependency on the previous state and so on. We are going to cover them later as a part of module 3, and eventually once we understand this, we understand some parts of how to build memory systems and so on in a very superficial way. Of course, we cannot cover all these things in great depth, but you will eventually understand things about how timings are done in a CPU and control is done, right? So module 2 and 3 will together introduce you to design of digital logic circuits. Okay, so one part will be combinational, the other part will be sequential. Once this is done, we will put them together as a part of your module 4, where we can get a bird's eye view of the processor design and instruction set architecture. So once you start executing some program on your designed CPU, you need some kind of a nomenclature about, or some syntax about how a person or how a user is going to execute code on your computer, because this is a computer that you are designing. It's not a computer that Intel has designed or Qualcomm or AMD has designed, right? This is your own circuit, your own CPU. So you need to tell the users a proper way to code or translate their software logic into your that is interpretable by your computer, right? So typically that is the instruction sets. We are going to know about instruction sets and how this instruction set architecture takes care of these things. Okay, and if we have time, we can go a little bit more deeper into the memory management. Of course, this will also be covered extensively as a part of your OS course. So this is the lesson plan, and we are going into the foundations of the digital world. Okay, so some of the foundational logic, what is meant by digital representing information and so on.